One atom plus two photons equals quantum computing switch. This IEEE article involves a paper entitled All Optical Routing of Single Photons by a one-atom switch controlled by a single photon, authored by the following people from the Department of Chemical Physics in the Weizmann Institute of Science, Israel. The focus of this paper is in the novel photonic switch. This consists of a rubidium atom positioned in one of two states. In the ground state, seen in figure A, we can define this as m sub f equals -1. When a photon moves from left to right, it is reflected by destructive interference with the photon emission from the rubidium atom. This interaction then changes the state of the rubidium atom. In the m sub f equals +1 state, seen in figure B, when a photon moves from left to right, it is transmitted undeterred. Each state is interchangeable depending on which side the photon comes from. The defined two states form the photonic switch. Next, figure A here describes the schematic of the photonic switch. For ease of understanding, we can define the two states of the rubidium atom as red and blue. In the red state, a photon from the right, or input 2, gets transmitted to the left, or output 1. A photon from the left, or input 1, however, gets reflected back to the left, or output 1, and changes the state of the rubidium atom to blue. In the blue state, a photon from the left gets transmitted to the right, and a photon from the right gets reflected back to the right and changes the state of the rubidium atom to red. We can see from figure B that information can be taken from the photonic switch with the use of SPCMs, or single photon counting modules, used to detect single photons leaving through output 1 and 2. This photonic switch can be a big step towards quantum computing, the theoretical, efficient potential future of computing. The key to quantum computing, and the goal the researchers aim to achieve with their photonic switch in the near future, is the qubit. The qubit, or quantum bit, involves the utilization of the uncertainty of certain physical elements such as the spins of single electrons, the electron states in atoms or molecules, nuclear spins in molecules and solids, magnetic flux, the spatial propagation modes of single photons, and the polarizations of single photons. We can illustrate the efficiency of the qubit with this figure. A normal computing bit has two states, 0 or 1, representing, say, the two states a transistor may take. A transistor is the switch used in modern computing. A qubit also has two states, 0 and 1, but can also take in any number of other states defined by the probability, alpha and beta, for the state to be either 0 or 1, respectively. Taking the two states as opposite vectors, the linear combination of the states with the probabilities can represent any point on the sphere, thereby granting the qubit many more states than just two, depending on the accuracy of measurement of the probabilities. We've probably realized by now that the qubit is much more efficient than the bit in terms of holding information. A related patent to this paper can prove to be a solution in making a qubit out of the photonic switch. Basically, the patent explains the use of an optical switch which accepts two photons. It transmits one and places the other into an optical loop. The photonic switch designed in the paper can act as the switch used, and the polarization of the photon in the loop can provide for the undetermined state, making a qubit.